Hey everybody, this is Miss Bufford, and in this video we're going to talk about the electromagnetic spectrum. Your learning goals are to be able to explain the electromagnetic spectrum using the terms energy, frequency, and wavelength, and to be able to explain how electrons of elements are related to the electromagnetic spectrum. So the first thing we're going to talk about is electromagnetic radiation itself. And electromagnetic radiation exists in a continuous spectrum ranging from gamma rays that have super tiny wavelengths all the way up to radio waves that have these gigantic wavelengths up to 100 kilometers. Electromagnetic radiation, or light, is composed of photons, and these photons are little packets or little discrete packets of electromagnetic radiation, and they move in a wave-like motion or pattern. And just like electrons, a photon is a type of elementary particle, which means that it's a particle that's not composed of any smaller particles. And they exhibit what's called wave-particle duality. And this means that they have, sometimes they can behave like waves, and sometimes they behave more like particles. And we'll talk a little bit more about that in a lab that we'll do as far as how we can tell the difference in what they do in order to behave like a wave or a particle. Although energy, wavelength, and frequency of the photons in the electromagnetic spectrum can vary, so that's what makes all of these different forms of electromagnetic radiation different, is just that they have different energy associated with them. And the energy that a photon contains is going to correspond to a specific wavelength and a specific frequency. So the speed that all of the photons of all of these different types of electromagnetic radiation move at is going to be the same, which is going to be the speed of light. All right, so they all move at the same speed, but the only difference between these is really the amount of energy they contain. All right, and so let's talk about some properties of this electromagnetic radiation. So wavelength is one thing that we're interested in learning about in this video. So a wavelength, if we take a look at this wave diagram down here, it's just a little depiction of a very simple wave. When we measure wavelength, what we're measuring is the distance between the crests on a wave, or if we wanted to, we could measure the troughs, the distance between the troughs, which is this lowest point here on the wave. But the distance between two crests or two troughs is equal to a wavelength. Okay? Frequency of electromagnetic wave is the number of crests or troughs that pass a specific point in a given amount of time. So if we have a high frequency, we have a lot of these crests passing in a certain amount of time. If we have a low frequency, then we don't have as many. And then energy, the energy of a wave is how energetic or how powerful that wave is. How much energy is it carrying? All right. So let's take a look at some relationships between these three variables. And so the first relationship we're going to look at is the relationship between energy and frequency. And so we take a look at our diagram over here. We see energy is right here. Energy is increasing as it's moving across the diagram this way, from the radio wave region to the gamma ray region. So we can see that gamma rays have the most energy and radio waves have the least energy. If we look at frequency is also increasing as we move across the this is not the periodic table, as we move across this diagram of the electromagnetic spectrum. So this is also going to be increasing in that same direction. And so what we have here is a direct relationship where one of the variables is increasing and it's causing the other variable to increase as well. And this works in reverse as well. If we start moving in opposite direction and energy is decreasing, moving closer down to radio waves, then the frequency will decrease as well. So this is true no matter which direction we're moving, whether we have a lot of energy or whether we have a little bit of energy. And then the next couple relationships we're going to look at are the relationships between energy and wavelength. So like I said, if we're moving this way across the electromagnetic spectrum from radio waves to the gamma ray region, our energy is going to be increasing, but our wavelength is going to be decreasing. And so what's happening here is we've got these really energetic waves, and as they get more and more energy, The frequency is also going to be increasing. And so when the frequency increases and the energy increases, those wavelengths get really tiny and close together. They're like really compact because the wave has a lot of energy. And so wavelength is going to decrease as energy increases. And so this is an inverse relationship where we have one variable that's increasing and another variable that's going to be decreasing. All right. And then the other relationship that is an inverse relationship is the relationship between wavelength and frequency. So again, we talked about a minute ago how, if the energy is increasing, the frequency is also going to be increasing because, as we pump more and more energy into that electromagnetic radiation, or as it has more energy, the frequency is going to get higher and higher because we have more crests passing that certain point in a given amount of time. And in turn, that's going to cause the wavelength to get very, very small because now our waves are just really compact, really coiled tightly together. And so that's just another inverse relationship. And again, this works no matter what. If we have one variable increasing, it's going to cause the other to decrease. Or we could say if one variable is decreasing, it's going to cause the other to increase. Either way we look at it. All right. But what does the electromagnetic spectrum have to do with atoms? Because this is chemistry, right? So let's take a look at some brief history. The evolution of our understanding of the relationship between matter and electromagnetic radiation began or came close to beginning in the 1700s when scientists first noticed that adding different salts to alcohol flames produced flames of different colors. And eventually this evolved into the use of prisms to separate wavelengths of emitted light. And in the late 1800s, a scientist named Johann Balmer discovered an equation that allowed him to calculate the unique wavelengths of light that were emitted by hydrogen. And at the time, nobody knew why elements emitted these different colors of light. Nobody could really explain it. And we'll leave it at that until we get to a couple slides from now. But I just wanted to show you a picture of this light that's being separated by a prism and what the emission spectra would look like. So in this setup right here, I have this gas discharge tube that contains hydrogen, and you can kind of think of this as like a neon bulb that's filled with hydrogen gas, and when we pass electricity through it, it causes that gas to glow. And when that gas glows, it's of course producing light, and we've all seen neon signs. They're kind of the same thing. But this light is being passed through this little tiny slit, and this slit is causing the light to go through this prism. And as the light moves through this prism, because this is a mixture of different wavelengths of light, when it passes through this prism, different wavelengths of light are going to bend at different angles because they're moving through that medium or that prism at a different speed. And so they're moving or bending at different angles, which is separating the different wavelengths of light that are making up the light coming from this hydrogen discharge tube. All right, and so they hit this black screen, and we end up with this emission spectra up here. And so you can see a little faint purple line, and I don't know if you can see it here, but there's a faint dark blue line right there, and then a bright blue line here, and then red. All right, so this is the emission spectra for hydrogen. So this is what people were seeing, and they were like, I don't know why I'm seeing this, but I'm seeing it. And then Bohr came along. When he developed his atomic model, he took into consideration the work of many other notable scientists, including the work of Johann Balmer. One of the things that Bohr proposed about atoms was that electrons could transition between different energy levels by absorbing or emitting electromagnetic radiation. And he proposed that the emissions that were being observed from these different elements and from hydrogen were due to these electron transitions, and the fact that they were, absorbing photons and spitting photons back out. And so here are some more details about what Bohr said. So electrons in an atom can only absorb enough energy to transition from one level to a higher energy level. All right, they don't stop anywhere in between. There's no way for them to stop in between. They they either absorb a specific amount of energy and they transition, or they don't transition. They don't absorb it and they don't transition. All right. So it has to be a specific amount, and the specific amount has to be equal to the distance or the energy difference between these different energy levels. And that's going to be different for every atom. All right. When an electron absorbs electromagnetic radiation or absorbs a photon, so in this picture here, you can see that this electron right here is absorbing this green photon and it's jumping up. This electron right up here is considered to be an excited electron because it's got extra energy and it's in a higher energy level than it normally would have been in. So it jumped up and became excited. Well, eventually this electron is going to emit that electromagnetic radiation. It's going to relax back down to what's called its ground state. And its ground state is the energy level where it was before it became excited. Right? It's its original home, you can say. So the ground state is where an electron is normally at. An excited state is when it's absorbed electromagnetic radiation and jumped up to a higher energy level. An electron can transition up or down, whether it's either emitting or absorbing electromagnetic radiation in one step, like one big step, either up or down, or it could happen in smaller steps. It could absorb one photon and then maybe absorb another photon and jump up again. And then maybe on the way down, it can emit just one big photon that's equal to that energy difference between the two energy levels and go all the way back down at once. Or it could emit several smaller photons that are all equal to the energy difference between where it started and where it's ending. All right. Whatever an electron does, though, if the energies of these photons correspond to wavelengths in the visible spectrum, then we can see it. But not all emissions occur within the visible spectrum, so it's possible to have emissions corresponding to any region of the electromagnetic spectrum. And one example of this is the hydrogen atom here. So if we have electrons starting in this third energy level right here, and they're transitioning up and then relaxing back down to the third energy level, they will emit infrared radiation, right? And we experience this as heat. If we have electrons that are transitioning from the second energy level, or n equals 2, and they're jumping up and then, being relaxed back down and releasing those photons, those correspond to wavelengths in the visible spectrum. So that's what we can see. And then if we have electrons that originated in the first energy level around hydrogen, and they're jumping up, absorbing that energy, and then re-emitting those photons, those are emitting light in the ultraviolet range. All right. So the UV range, and those are called the Lyman series. Balmer series is in the visible spectrum, and the Paschen series is in the infrared spectrum. Okay. So every element has its own unique emission spectra because each element's energy levels have unique energies associated with them. And these unique energies are due to the different numbers of protons in the nucleus and their influence on those electrons in the electron cloud. So how tightly they're being held, how closely they're being held. And the emission spectra is kind of like a fingerprint for an element, so it can be used to identify different elements or even compounds. And so I've got some basic emission spectra shown here for just some elements from the periodic table. Those are pretty neat looking. And one other thing I thought was super cool was this periodic table that has all the emission spectra on it for all the elements that we have emission spectra for. So I thought that was pretty neat, and I just wanted to show it to you. But thanks for watching Buffered Chemistry. Subscribe to my YouTube channel for more chemistry help.